In Activity 10, a motor model, students apply what they observed in the previous activity about a simple motor to build a more complex motor. They infer the relationship between rotating electromagnets and fixed permanent magnets, and then determine the function of brushes in a motor. You will need the following materials from the kit: Activity Sheet 10, D-cell batteries, motor brushes, T-shaped copper strips, delta circuit workspaces, electrical clips, emery cloths, foam cylinders, rubberized magnets, paper fasteners, rubber grommet spacers, plastic rods, 25 centimeter plastic insulated wire pieces, 15 centimeter plastic insulated wire pieces, roll of enamel-coated wire, wire cutters, and masking tape. You will also need to provide metric rulers. To prepare this activity, make a copy of Activity Sheet 10 for each student. Cut 2 pieces of enamel-coated wire 3 meters in length for each team. Each team of students will need a plastic base, a foam cylinder, a plastic rod, 2 3-meter pieces of enamel-coated wire, a piece of emery cloth, 10 rubberized magnets, 3 batteries, 2 15 centimeter and 2 25 centimeter pieces of plastic insulated wire, 4 rubber spacers, 6 unbent electrical clips, 2 paper fasteners, 2 brushes, 2 strips of masking tape, and a metric ruler. To begin the activity, inform students that they are going to apply what they have learned in the previous activities to build a more complex motor. Remind the students that the rotation of the armature in the simple motor was caused by the on-again, off-again interaction between the electromagnetic field of the armature and the magnetic field of the permanent magnet. Demonstrate for the class how to assemble the armature for the motor that will be constructed in this activity. Start by pushing the foam cylinder onto the plastic rod so that it is 5 centimeters from one end of the rod. Rotate the cylinder so that its grooves line up with the grooves in the rod. Hold the rod so that the long end is pointing toward you. Then, leaving about 10 centimeters of one end of a 3-meter wire free by the long end of the rod, begin winding the wire around the cylinder using 2 opposite-facing grooves as guides for the wire. While winding, wrap the wire on alternating sides of the rod, keeping the wire as tight as possible. Continue winding until the ends are of equal length and then pull the loose ends toward you so that they run along the length of the long end of the rod. Sand off 9 centimeters of enamel coating from each end of the wire. Once the sanded ends are in position in their respective grooves, use a piece of tape to hold them in place close to the armature. This completes the first coil. It is important that each sanded wire end aligns with the groove in the rod as well as the coil from which it originated. After the coil is completed, you may need to sand and/or trim the wire ends so that you end up with 2 sanded wire ends of equal length. Repeat this procedure with the other 3-meter piece of wire and the 2 remaining grooves in the cylinder and rod to make the other coil. Be sure to wrap the wire on alternating sides of the rod. After completing the second coil, sand and tape the loose ends to the rod. The sanded part of these 4 wires should be spaced evenly around the rod so that they do not touch each other. Next, slide a rubber spacer onto the long end of the rod so that the wires are between the spacer and the rod. Push this spacer all the way to the foam cylinder. Then attach the second rubber spacer, push it to 2 centimeters from the end of the rod, and fold the ends of the wire over the spacer. The finished armature should resemble the one shown in Figure 10.3. Distribute a foam cylinder, a rod, 2 rubber spacers, a metric ruler, a piece of emery cloth, 2 strips of masking tape, and 2 3-meter pieces of enamel-coated wire to each team. Then, have students assemble their armatures. Next, distribute Activity Sheet 10 to each student and the circuit works base, batteries, electrical clips, 15 and 25 centimeter lengths of wire, motor brushes, paper fasteners, rubber spacers, and magnets to each team. Discuss the procedures in steps 1 through 6 and have the students construct their motors. The students should position the magnets so that they stand on their short ends. This puts the magnetic field at the same level as the coil. In the event that a motor does not work, follow these troubleshooting tips. make sure that the sanded part of the wire ends from each coil are opposite each other on the rod so that the brushes will energize the correct wires and only one coil will be energized at a time. The portions of wire between the rubber spacers must be sanded bare, and the armature must be able to rotate freely between the two stacks of rubberized magnets. The students can test their motors by touching the ends of the two 25-centimeter battery connection wires to the sanded parts of two wires that are on opposite sides of the rod. This contact should create an electromagnetic field around one coil and make the armature move. Have the teams work together to review their setups and compare them with the diagram on the activity sheet. The strength of the armature's electromagnetic field is dependent upon the number of coils of wire wrapped around the foam cylinder and the amount of current flowing through the coils. The strength of the permanent magnet's magnetic field is dependent on the number of magnets in each stack and their distance from the armature. Begin a class discussion by explaining that in this motor, the armature consists of the foam cylinder with the two wire coils wrapped around it. Then tell students that in this motor, the brushes are the two T-shaped pieces of metal attached to the base. Ask students, what is the purpose of the two brushes? The students should infer that the brushes are the contact points between the current from the battery and the armature coils. The brushes make an electrical contact with the sanded wire ends of the armature coils, causing an electric current to flow through the armature coils. Next, ask students, what happens to the coils when the electric current passes through them? Ask a student volunteer to trace the path of the current, first through one coil and then through the other coil. As the current flows through one coil, that coil becomes an electromagnet. Its electromagnetic field interacts with the magnetic field of the rubberized permanent magnets, causing the armature to turn. By turning, the sanded wires of this coil move away from the brushes, opening the circuit and turning off the electromagnetic field around the coil. But turning also brings the wires of the second coil into contact with the brushes, closing the circuit and creating an electromagnetic field around the coil, which, in turn, interacts with the permanent magnets and continues the rotation of the armature. Finally, ask students, what modifications could you make to your motor to make it run slower or faster? The students should realize that both the strength of the magnetic field of the permanent magnets and the strength of the electromagnetic field of the armature affect the motor's speed. To conclude the activity, have the students disassemble their motors, including the armatures, and return all of the equipment to the kit. Discard any dead batteries. For science background, reinforcement activities, curriculum connections, and information about the Delta Science Reader, please consult your DSM Teacher's Guide.